I'm going to introduce an idea called binding energy. Energy is released when a nucleus is formed. Okay, so energy is released when a nucleus is formed. Now what's nucleus formation? That's nucleons being bound together. So if you've got an isolated proton, neutron, neutron, proton, when these bind together, energy is released because a nucleus is formed. Now the more energy released, the more stable the nucleus, which makes sense because, you know, anything that releases all its energy is then going to be pretty relaxed, isn't it? So it'll be nice and stable. Same with if you've got a ball sitting up here, it's on the edge of this cliff here, it's pretty unstable. It's got a lot of energy though, it's got a lot of gravitational retention energy. If it then falls down, it will eventually just come to rest. You'll have far less energy, but it will also be stable. Okay, so that explains this relationship. The more energy released, the more stable the nucleus. And we call this energy the binding energy, which makes sense because the energy released when a nucleus is formed, i.e. nucleons getting bound together. Let's have a look at this graph. So this is a graph that's all about binding energy. So again, let's look at the two-axis. The y-axis says the average binding energy per nucleon. It's in mega electron volts, which I will show you how to convert between in a second. So it just tells you how much bonding energy is in, on average, each nucleon per element. So for example, helium-4 right here has, on average, 7 mega electron volts per nucleon. It's got 4 nucleons, so it must have 28 mega electron volts of energy as you know, when its nucleus gets formed. So when you make a helium nucleus, it releases 28 mega electron volts. Okay. So let's have a look at formation of a nucleus. Oh, let's look at one other thing. Look at poor old hydrogen 1 here. It has 0 binding energy, which is obvious because it's only 1 nucleon. It's not bound to anything, so how can it have any binding energy? That's what explains why it's 0. So let's look at a common nuclear reaction. So this is fusion, nuclear fusion, because fuse means to join nuclei together. So 2 of hydrogen 2 plus another hydrogen 2 makes a helium-4. So if we had, this is what it would look like. There's 2 nucleons, one of the proton. This is 2 nucleons as well. One's a proton. This is 4 nucleons, and 2 are protons. So that's what's happening. Now I just told you before, building a nucleus or forming a nucleus releases energy. So therefore, if we ever break these apart to then form this one, we're going to cost energy to do so. So if we look at, here it is, hydrogen 2, and helium-4, that's what we're looking at. You're going to see that we release quite a bit of energy in this reaction. So hydrogen 2's binding energy is about 1 mega electron volt. So this is 1 mega electron volt per nucleon. There are 2 nucleons, so that's going to be times 2, so that's 2 mega electron volts. This one is hydrogen 2. Okay, again, about 1 mega electron volt per nucleon. Then times it by 2, and that will give you 2 mega electron volts. So far, that was breaking apart, therefore cost energy. Okay, so 2 mega electron volts, 2 mega electron volts, that costs us 4 mega electron volts. To break these down so that we can join them back together to make helium. Now helium-4, okay, so helium with 4 nucleons, that's about 7 mega electron volts per nucleon. 7 mega electron volts per nucleon. Okay, and there's 1, 2, 3, 4 nucleons in that helium nucleus. 7 times 4 is 28. And that's released. So therefore, overall, we have 28 released, but it cost us 4. So we lost 4, so that's overall 24 mega electron volts released. And that's why fusion releases energy. Okay. What's the most stable nucleus? Well, it's the one that releases the most energy. So it's got to be iron. It releases, on average, the most energy per nucleon involved. What about fission? Well, here's uranium. It can turn into, say, strontium and xenon. And check it out. Uranium, we have to break a uranium apart, which would cost us energy. But then you're forming xenon and strontium, which are higher up the energy diagram. So forming these two nuclei, we're going to release more energy than it cost us for breaking uranium down. Let's just say that we tried to fuse plutonium with, I don't know, something up here, plutonium and copper or something, to make uranium. Well, plutonium and copper are both higher up the energy ladder, so if we're going to break those down and then reform uranium, it's going to cost us more energy to break these two down than what we'll get back when we form uranium, because it's lower down the energy ladder. Same if we try to do fission with helium and break it down to hydrogen. Well, helium has 7 mega electron volts per nucleon, so that's what's going to cost us to break it down. And when we reform hydrogen, you're only getting 1 mega electron volt per nucleon back released into the surroundings, so it's not going to work. So while fission and fusion both are able to be done to release energy, you've got to be careful what you're fissioning and what you're fusing for it to actually get a successful energy release, which is what you're going for. Okay. Other things to think about that you can research on your own is this like crazy spike. This is a massive anomaly here. Look at this trend line. We're going up, 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 curves off, down and down and down. Pretty smooth, except for helium. There's a couple of other little anomalies here as well, but that helium one's crazy. So you should look into what's caused that if you want to do a complete analysis of this graph. Okay. Yeah. You don't have to be able to do this. This just hopefully helps you understand the relationships, and I only use the numbers there to illustrate as an example to help my explanation of this graph. Okay, but please don't include, this doesn't have to be included in your assignment at all.